Welcome everyone. Now we will look at the convolution integral. In the previous lesson, we looked at the discrete time version, the convolution sum. So for continuous time systems, we have the convolution integral. Similar to what we did in DT, in this section, we will obtain a complete characterization of a continuous time LTI system in terms of its unit impulse response, which we symbolize as HT. In discrete time, the key to developing the convolution sum was the shifting property of the dt unit impulse, that is, mathematical representation of a signal as a superposition of scaled and shifted unit impulse functions. So we begin by considering the staircase approximation x hat t of a CT signal xt. So in this picture, you can see xt. So what we represent in black is xt, and we have approximated xt with this staircase function x hat t. So what you want to do is break this x hat t into square pulses. Okay, now let's take an example. The square pulse from minus 2 delta to minus delta. That has the value at minus 2 delta. So therefore the height is x minus 2 delta. It goes from minus 2 delta to minus delta. It is very important not to just have this number, which is a constant in regard to time, but have this time function delta delta t. So if we remind ourselves what delta delta t is, it is actually 1 over delta. The height is 1 over delta whenever our t is between 0 and delta, 0 otherwise. So you can see we can have located a delta delta function at x minus 2 delta, t equals to minus 2 delta, and we have multiplied that by delta because its height is 1 over delta. If you just take, for example, wt equals x minus 2 delta, you can see this is a constant. That means it is independent of time. So therefore, if you plot that, so you will have a constant x minus 2 delta with value x minus 2 delta. So that is why it is very important for us to multiply that by delta delta t plus 2 delta times delta in this case. So now let's look at the next square pulse. So it is of height x minus delta, and we represent that as x minus delta 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 t plus delta times delta. Okay, so now similarly we can represent this these square pulses, and then what we do as before is summing them. When you sum them, you actually get this signal x hat t, which is in red, an approximation of xt. Okay, so here you can see this number 2, 1, 0 and minus 1 and so on. K changes, and we have to sum that over that particular value k. So we can consider in general this is x k delta is this value, and this we can represent as delta delta t minus k delta or something. Okay, so therefore we have this representation x hat t is equal to k goes from minus infinity to infinity x k delta 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 t minus k delta delta. So therefore this thing is independent of time. That's why we call it a constant or a constant multiplier. So the multiplier of this linear combination of these basic signals. So these are the basic signals. So we choose this basic signal so that it is easy for us to compute the output of a system due to that signal being the input. So here for any value of t, only one term in the summation on the right hand side is non-zero. What's the reason for that? So for this delta t to be non-zero, so the argument t must be from 0 to delta. So therefore only for one value of k it is so, and then this becomes sort of active only within that interval. So only one term is active. Okay, so when we send delta to set the limit to 0, then we can convert that into an integral. You can see xt is equal to minus infinity to infinity x tau delta t minus tau deta. So this is known as the shifting property. What have we done? We have represented xt as a linear combination of basic signal. So this is that basic signal. You can see it is a function of time, and these are constants. Constants if we consider time. So these are constants, and they are actually the sort of the multipliers in the superposition. Okay, now we have represented the signal. Now what we need to do is to apply that to a system and try to compute the output. So before that, we will take an example using shifting property, express ut in terms of delta t. So ut is integral from minus infinity to infinity. You can see u tau delta t minus tau d tau by using this expression. X tau delta t minus tau d tau. Here you can see as u tau is non-zero from 0 to minus infinity to 0. You can write it like that, and during this interval it is equal to 1. Okay. So let's move forward. The continuous time unit impulse response and the convolution integral representation of an LTI system. So let's define h hat k delta t as the response of an LTI system to input delta delta t minus k delta. So what we are saying here is, so we have that system. The input to that is this one, that means delta delta t minus k delta. So we say that due to this, our output is h hat k delta t. So we use this as a subscript to indicate that it is a different shape of a signal due to the input at k delta. So therefore we can compute the output if the system is linear by getting the same linear combination in the same multiples. So the multipliers are xk delta as you saw before, and combining the output. Okay, since the pulse delta delta k minus k delta corresponds to shifted unit impulse, as delta goes to infinity, the response h hat k delta t to this input impulse becomes a response to an impulse in the limit. So this is actually h tau delta is what I wanted to say, I think. Yes. So what we say is in the limit, this we can write as delta t minus tau, and for that the output is h tau t. So you see the output shape depends on tau. Okay, so in the limit, so when delta goes to 0, so we can have the integral yt is minus infinity to infinity x tau h tau t d tau. So you can see it depends on that time delay. Now we have only applied linearity up to now. So this is similar to what we had in the shifting property. So you can see when x is given as the input, this one results in this output. So that's how we can write it as a linear combination. Okay. So this is a pictorial representation of that. Okay, so in addition to being linear, if the system is time invariant, the response of LTI system to the unit impulse delta t minus tau becomes, the shape does not change with tau, but it is just a time delayed version of the shape at tau equals 0, just time delayed by that. So since we are lazy, we will drop this 0 and call it ht. So therefore we have yt equals minus infinity to infinity x tau ht minus tau d tau. This is the all important convolution integral. which is referred to as a convolution integral or the superposition integral. This corresponds to the representation of a continuous time LTI system in terms of its response to a unit impulse. So we represent that as the convolution. This is the asterisk symbol. So yt is xt convolved by ht. As in discrete time, a continuous time LTI system is completely characterized by its impulse response, that is by its response to a single elementary signal, the unit impulse delta t. So if we just juxtapose this with the discrete time version, yn is equal to summation k goes from minus infinity to infinity xk h n minus k. So you see they are very similar. So instead of xk you have x tau, instead of h n minus k you have h t minus tau, and of course the summation becomes an integral. So once again, to compute one value, example yt equals 2 seconds, we need to carry out an integral from minus infinity to infinity. So in this equation, consider t as a constant. Then we have to compute the value of yt at every single t. Of course, in practice, you know that we can write general expressions. So as in discrete time, a continuous time LTI system is completely characterized by its impulse response ht, that is by its response to a single elementary signal, the unit impulse delta t. Okay. So we can take examples. Let xt be the input to an LTI system with unit impulse response ht, where xt is equal to e to the power of minus at ut, a greater than 0, ht is ut. So we can plot these singles. This is our h tau. So remember, in the expression, what we want is not actually ht, but what we want is h tau as before. So that's why we write it in this fashion. Yt equals minus infinity to infinity x tau h t minus tau d tau. Okay. Then we have x tau and h t minus tau. So therefore, when you represent ht like this, you have to reflect it at the time origin to get x minus tau, and then t is a constant, so t is here. So you can see how we represent these two signals. Then we have to multiply x tau and ht minus tau, and then do the integration. So we have to see when do these two signals overlap. Right now, if we just multiply them, the multiplication turns out to be 0, because during this interval this is 0, and here it is 0. Okay, so it is non-zero only when t is greater than 0. When t is less than 0, the output is 0. So therefore, for t less than 0, the product x tau and xt minus tau is 0. Consequently, yt is 0. For t is greater than 0, x tau ht minus tau turns out to be e to the power of minus a tau, and tau is from 0 to t, as you can see from here. All right. So this is that exponential decay that we see, e to the power of minus a tau. That gets multiplied with that during this time interval. Okay, then we can carry out the integration. So 0 to t e to the power of minus a tau d tau, that is minus 1 over a e to the power of minus a tau, limit 0 to t, and then you have this expression. So then to write yt for all t, because to combining this part and that part, we can write yt is equal to 1 over a 1 minus e to the power of minus at ut, because ut is this. Okay, that completes the example, and here is the plot of that. Okay, so we can take another example. Consider the convolution of the following two signals. Xt equals 1 between 0 and t, and ht is equal to t between 0 and 2t, and otherwise. So this results in a cumbersome tedious work that we had to do. So this is x tau, it is 1 from 0 to t, and then this is ht minus tau in red. So I have plotted xt also in a dotted blue line just for you to see. So x t minus tau, you can see our ht was given as this until 2t, height is 2t. Actually this height I should have written, this height should have been represented differently, but that's okay. Okay, so now there is no overlap. Now if you move it slightly, that means if t is greater than 0, there is an overlap over here, small t. And then when small t is greater than capital T also, this is capital T, there is an overlap over here. And again, there is an overlap from t minus 2t to t in this case. So we have to consider this scenario, and this, and carry out 3 different integrations. Okay, here the overlap is 0. Okay, so I have drawn them again. So here you can see this height is t, and we know this distance, so therefore the area is half t squared. Half t squared. So I shouldn't have written this as 2t, I think. That's wrong. Just given as 1, yes. Okay, so for this the area, you can see you can write this area as tt minus half capital T squared, and then this area also you can compute like this. So with this we can write yt as this. When t is less than 0, it is 0. When t is greater than 3t also, it is 0. Otherwise you have these values. So I have plotted that in dark red. So then find yt, the convolution of the following two signals, e to the power of 2t u minus t, xt ut minus 3. So this is e to the power of 2t minus u minus t. So we know that u minus t is like this. There you go. So x tau is equal to e to the power of 2 tau u minus tau t. So this is that signal, and then we have xt is equal to u t minus 3. So this is that signal with in the tau axis, and it has been reflected and plotted. So take some time to think about it and verify that this is the case. So now you can see if you compute yt, you will get a form like that. You can see where the overlaps are. It always overlaps. So from here, now in this case you have to integrate up to t minus 3. So then after that the value is constant. You will see when t minus 3 is greater than 0, you can see there is full overlap. That means when t is greater than 3, it is a constant. So you can verify this on your own. So when t minus 3 is less than 0, the product x tau and ht minus tau is non-zero for minus infinity to t minus 3, and the convolution integral becomes minus infinity to t minus 3 e to the power of 2t d tau, that means half e to t minus 3. Okay. For t minus 3 greater than 0, the product x t tau ht minus tau is non-zero for minus infinity t to 0, and the convolution integral becomes minus infinity to 0, that is half. Okay, that's what we do. Okay, next time we will look at properties of linear time invariant systems, that means relating ht and hn to the properties of linear time invariant systems. Thank you.